I think,
I just started the recording
yeah,
process. Let's see here.
I think the best approach is to ask all the
Uh,
presenters to turn their videos on, so then we can go from that, I guess. Okay, so this is the software engineering practice. Oh, Nancy's here. Okay. Hi,
Yes,
Nancy.
yes, I'm
All right.
here.
All right.
I had
Okay.
I had a little trouble logging in.
All right. No problem. I'm going to then turn off.
Okay, excellent. Well, thanks for joining us. This is Software Engineering Practice, Session 3. We'll be at this for an hour. We have 30 minutes of presentations followed by 30 minutes of discussion. If everyone is here, then we will have 6 presentations of 5 minutes each. It would be helpful if people who are not presenting at a particular time would all mute their microphones, and I will do the same thing. I suggest that we use the chat session for comments and questions, and we will address as much as we can in the second part of our hour. I'm also going to ask each speaker, after I introduce them, to identify themselves again, because I'm pretty sure that I will get some of the pronunciation of your names wrong, and I want everybody to hear what it is correctly. I would also like to mention that I spent the first half of my career as a developer and management of software products, especially large real-time systems. So this subject is very near and dear to my heart. With that, let's get started. Our first speaker is Jo-Yeon Yoon, and she will be presenting automatically identifying shared root causes of test breakages in SAP HANA 2.
Okay, I'll share my screen.
That'll be wonderful. And I'll mute my microphone.
Could you see my screen? Yeah. Maybe it looks fine. So
yes, we can see it.
Okay. Hello, everyone. Today, I'm going to present our paper, Automatically Identifying Shared Root Causes of Test Breakages in SAP HANA. And this is our presenter, Jo-Yeon Yoon. So let me start with explaining the post-submit testing process performed in SAP. So the test run is performed once a day, aggregating all code changes together. And after the test breakages are identified, a bug ticket is manually assigned to each breakage. But this kind of manual labeling can generate duplicated bug tickets, resulting in unnecessary review effort. So we propose a technique to identify shared root causes and merge the duplicated bug tickets. So how can we know that if 2 breakages share a root cause or not? The main assumption behind our approach is the more similar two tests are, the more likely they are to share a root cause. And the next question would be, how can we measure the similarity between the test cases? We chose to use different types of information and calculated similarity between the processed information, which are from the 3 categories, which are static, historical, and dynamic. So for static information, we used test case names. We can either use normalized edit distance or measure the cosine similarity between the vector representations. And to process the historical information, we extracted binary vectors from the execution history. And we used first fail and pass test results, and next the transitions in the test results. And for dynamic information, we used test case coverage. So diverse similarity metrics can be used here, but we additionally adopted hypergraph-based similarity. By this, we aim to compare the root causes between the failing tests in more effective way. Our experiment uses 27 similarity function configurations in total, and by collecting 6 months of test results, the first 3 months were used for training, and the later 3 months test dataset. And we first compared the effectiveness of each similarity function. The effectiveness could be measured using average precision, which can be calculated from the area under the precision recall curve. And according to AP score, we found the best performing configuration for each information source. In the actual classification scenario, we need to set a fixed similarity threshold. However, the learned threshold from the training data do not generalize well to the test data, and this could be a limitation of using single similarity function individually. And if we compare the Venn diagrams of correctly classified pairs, they are in fact complementary to each other. So now we can think of using all information sources together. To do this, we train a classification model that accepts all the similarity function values and predicts the binary labels indicating whether the two tests share the root cause or not. We also confirm that the classification model outperforms all single similarity functions. The combination of PCA feature extraction and Baking ensemble model was the best performing one among the various model configurations. To conclude, we first revisit our aim to reduce the redundant bug tickets, and by identifying shared root cause of test breakages. And there were 3 types of usable information to represent the failing test, the breakages. And we propose a classification model integrating the various similarity functions. Finally, we evaluate our technique on the real-world test history, which were collected from SAP HANA. And thank you for your attention, and I'll be happy to take questions later.
Thank you very much. We'll just move on to the next presentation right now. And that is going to be given by Jianchao Liu. The talk is called Record and Replay of Online Traffic for Microservices with Automatic Mocking Point Identification. So, Jianchao, you're on. You want to unmute your microphone.
Yeah. Can you hear me?
Go ahead and share your screen.
Yeah. Okay, so my name is Jianchao Liu, and I'm from Ant Group. Today I'm going to present our work, record and replay of online traffic for microservices with automatic mocking point identification. So first, what is record and replay? So record and replay is to first record the online traffic, which is the inputs and outputs of the last version of a microservice. And then in the offline environment, you replay that traffic on the new version and to see whether the output is the same with the online version. So this can be taken as a regression testing. It's very popular actually in the industry. Okay, but there are some problems with the record and the replay because there's some undecidability in the programs. And this undecidability can make the same version of the microservices behave differently in the online environment and the offline environment. We classified such state dependencies into three categories. The first is the internal state dependency, which is some like static variables, because the static variables can change during the execution of microservices. So different threads can change it, and then in offline and the online environments, the value of it is not predictable. The other is the external state dependency, because in microservices, sometimes you can call other microservices. You can access all resources outside the application itself, like a remote procedure call. And then such calls can also be different in the online and offline environment. And so last one is the system state dependency, like the system functions, which returns the date of the returns the date, and also like the random values. So such state dependency make the even with the same version of the microservices, the output can be different. So what we do is that we fix this problem by mocking, which is to record not only the input and output of the microservice, but also the input and output of the function that have state dependencies, like the so that we replace the input and output of that function in the offline environment, so that we can have exactly the same output in the offline environment as in the online environment. But the problem is how to find such mocking points. In the industry, one common practice is to do that manually. So in one microservices, there can be tens of thousands lines of code and tens of thousands methods. So programmers need to manually identify maybe hundreds of mocking points. That is very labor consuming. It will take maybe some weeks for this for one single microservice. And as the application evolves, we need continuous work efforts to maintain the mocking points. There are some automatic identifications mocking points, but they don't. They're not applicable in the microservices environment. So because there are some challenges. The first challenge is that we only allow AOP level record and replay, so we cannot change any value of the static variables in the online environment. And another challenge is that we need to be sound. Like we have to find all mocking points, because any missing mocking points will make the recorded traffic unusable. And the other is the performance. So because in the online environment, the mocking, the recording process affects the performance. If it affects the performance too much, then it will affect the user experience. So too many mocking points will make the user experience, will make the user experience suffer. So we don't allow too many mocking points in our recording process. So like some system function cannot be mocked directly because there are too many of them. So our solution is that we first identify all system internal and external state dependencies with syntactic checking. So this step is easy, but we need to put all our the developer's experience into this checking, and then we find the mocking points according to these dependencies via taint analysis, because some state dependencies like the system call cannot be mocked directly. So, but with taint analysis, we know that which function is influenced by these dependencies. And another contribution is that we minimize the scope of mocking points via call graph, so that can reduce the number of mocking points further. So I will go with a simple example. Here we have a system function which is random. So we cannot mock the random function directly in the online environment. But we can do is that we can use the taint analysis to find out which function is affected by this random system call. The result is the sample method, which is because we can see that a random here it affects the return value of this method. Another function is the get number, because because the random value flows into the field number in this class, and then we found out that the return value of get number is affected by this field, which is from a random number, so that we can find 2 mocking points from this example. Okay, so for more technical details, please refer to our paper. So we have implemented it with GraalVM and deployed it. So it has been serving around 200 applications, which is 200 microservices. Each of them contains about maybe 10,000 lines of code to 1 million lines of code. So it has successfully generated more than 90,000 mocking points with a precision more than 97% and the recall more than 98%. So here is the conclusion that we identified all state dependency of industrial microservices, and we found the mocking points via taint analysis, and the result of mocking points only takes less than 20% performance loss in the production environment. Okay, thank you very much.
Thank you very much. We'll go on to the next presentation by Zhexin Zhang. Scalable compositional static taint analysis for tracking sensitive data on industrial microservices. And I know there was a name change between the paper and the presentation. When you start, perhaps you could let us know which is the correct name of the paper so that we can look it up. Thank you.
Okay.
I will mute. I can see
you
this.
guys see my screen. Okay. Hi, I'm Zhexin Zhang from Ant Group and the University of Technology Sydney. This talk, I'm going to share our paper on field-based steady taint analysis for industrial microservice. Taint analysis is the typical technique which has been used to trace the data propagation in the program. Many steady taint analyzers are proposed, such as FlowJoy, AntTaint, F4F, and GeoInfer. However, when we try to use this analyzer on the industrial microservice applications, we find that all these existing tools cannot analyze efficiently and precisely because of the following challenge. First, The recall rate of most existing analyzer is low because of the incomplete choreograph, which is used for inter-procedure analysis. Most existing steady tender analyzer run their analysis based on the pre-built choreograph. However, it is hard to obtain a complete choreograph statically in microservice application because of the usage of the complete framework behaviors, such as the AOP, IOC, and message service or event call. Even though we can supplement the choreograph by manually modeling these framework behaviors, it is costly and time-consuming, and it is hard to guarantee all framework behaviors are parity mode. If any framework behaviors is missed, the caller-collier relation will also missing in the generic choreograph, and the recall rate of the tender analysis will reduce. Scalability is another obstacle for steady tender analysis. Even though it is possible to get a sound and a precise choreograph, the obtained choreograph will be very huge because of the large scale of the microservice application. It is costly to run the precise context-sensitive inter-procedure analysis on such large-scale choreograph. And what is worse, the memory usage could be already huge if the HEP is abstracted precisely for instance with field-sensitive analysis. Precision is another significant concern for steady tender analysis. The tender analysis result of most existing tools are usually over-tainted due to the lack of tender checking in complex container like map, list, or JSON object. To solve this challenge and make the tender analysis available for the microservice application, we propose a field-based steady tender analysis solution. Compared to field-sensitive analysis, our field-based analysis relies less on the pre-built choreograph, which could provide better scalability and recall for chasing sensitive data. The field-based analysis doesn't distinguish different instances of the same type, but distinguish fields of the same kind. By merging all usage of the field in the microservice, we are able to perform the inter-procedure analysis without the pre-built choreograph. For example, in this case, the sensitive field of the class mode is seen as the same everywhere in the program, which will be merged in the field-based analysis. Therefore, why existing analyzer fail to find the data leakage at the interceptor when the interception mechanism defined in the Spring XML file are no parity mode? Our field-based approach could still find the sensitive field that propagate to log in the interceptor without any modeling of the interception mechanism. Our experimental result of the analysis on the production benchmark at Ant-Group demonstrate that the field-based analysis could run efficiently on large industrial microservices in minutes level. It is also worth to mentioning that our investigation into the industrial application found that each field usually represents a concept that keep unchanged in all its usage in an application. So sensitive data is usually propagated among the field assigned with a specific concept. This phenomenon undermines the precision loss of the field-based analysis compared to the field-sensitive analysis. Furthermore, we also improved the precision of our tools by modeling the operation of the frequency use container to support the field-based algorithm to chase the sensitive data precisely within container. So, in conclusion, we have introduced 3 challenges for steady tender analysis on large-scale industrial microservice. The low recall rate that caused by the unsound choreograph because of the miss of the framework behaviors. The scalability challenge which result in the cost in both memory usage and the time consumption. The precision challenge that caused by fail to chasing sensitive data propagation among complete container precisely. We have proposed our field-based analyzing approach, which doesn't distinguish different instances of the same type, but distinguishes fields of the same kind. It relies less on the pre-built choreograph than field-sensitive analysis. In our field-based analysis, we also improved the precision of the analysis by modeling the operation of the frequency use container. This is all of our talk. Thanks for attending.
Thank you. We'll move on to the next presentation by Sun Chao, a cross-company ethnographic study on software teams for DevOps and microservices, organization, benefits, and issues. I know you're here. I see you right here. So if you could take over and share your screen, that would be perfect.
Okay. Please wait with me a moment. Hello everyone. Do you see my screen?
No, we see you, but not your screen.
Okay, please wait.
Vinicius, do you have a suggestion for how to help him?
So, well, according to what I know, first the browser will request permission to share your screen, and then if you're using Windows 11 or Mac OS, I think there might be some kind of problem because you have to, yeah.
Uh-huh. Okay, we're all set. Carry on.
Could you hear my voice?
Yes.
That's perfect.
Okay, thank you. Hello everyone. It's my honor to be here to introduce my research. The title of my speak is a cross-company ethnographic study on software teams for DevOps and microservice, the organization, benefits, and issues. My name is Xin Zhou from Nanjing University. Emerging from the Angel developer communities, microservice, which is the portmanteau of micro and service, was considered as architecture solution for continued architecture settings in DevOps. Microservice achieve benefits by decomposing the maintenance into small services that communicate with each other through live-wire machines. Both DevOps and microservice have received increasing attention from researchers and practitioners over the past decade. The Google search trends for the two concepts since 2010 with a high degree of the consistency. They are commonly adopted and implemented together in many software companies. Our study aims to explore the organization benefits and issues of the software teams using DevOps and microservice in industrial contexts. With objective, the following research questions are formulated to guide this ethnographic study. Researchers in order to understand DevOps and microservice in software teams by investigating the daily reality of individuals or teams in various environments. So also a member of interviews with the practitioners and some observations on the participants were conducted in some relevant empirical studies. They are mostly carried out with researchers' applied experience, thus ignoring some small but key influence factors in practice, especially from the human and social aspects. This ethnographic studies increases the possibility of meeting important moments in the research process through the analytical participants or researchers in the software teams. The bicycle unit of software development to conduct participant observation and interviews. This research project began in January 2020 with a total of 7 months of participant observation in the 3 companies at different scales. They differ in business, size, product, customer, and degree of globalization. All 3 companies claim to use DevOps and microservice. Therefore, they offer similar environments in different state of the corporation development, which allows comprehensive information to be observed in the period of this study. In the data analysis phase, we mainly use the ground zero, one of the methods to build zeros and construct the reality in software engineering through the interactions with the language and communications was employed as a data analysis technique in the ethnographic study, since it provides a systematic method for generating conceptual zeros from the qualitative data source. Also, the 3 companies have different business settings. The organization of their software team could be similar structured as a 3-level structure, which brings changes to technical-driven changes and culture postments. We need mostly technical-driven organization. The technical-driven innovation requires a 4-level chain of group team, department, organization. On the top 2 levels, development and organization, the technical is often not the top concern and option to solve this problem. Affected by the solution by the stable organizational structures when using DevOps and microservice for software development. The software team may work as a virtual team. This picture shows the workflow of a typical virtual software teams for company 3. Each microservice is maintained by the virtual team composed of the engineers who may take on tasks in different development teams from 5 teams, which also achieves the combination of development and operations. Repeat integration and development are the major benefits from the perspective of the organization, which allows them to create value to market quickly. Both DevOps and microservice contribute to these benefits. Handleability and skills. This can be recognized as the main benefits for individuals that could help them to consider new job opportunities. It results from the requirement that a single team had to be capable for almost the full spectrum of responsibility in the entire life cycle of DevOps. Another possible reason is that team turnover is likely to be higher in DevOps. A reduced burden, this benefit can be dropped into microservice. Microservice also allow developers to focus on specific domains. The feature helps increase the happiness of software teams. However, the benefits enhance ability and skills of DevOps, which requires developers to take on more tasks, may have a negative impact on this. The high cost might be the most significant pain brought by both DevOps and microservice, similar to the problems arising whenever a new technical or method is adopted. Feels more locating issues in software in microservice also lead to a high time cost, where data consistency need to be granted while resolving these problems. Lack of participate guidelines. This pain is especially significant in microservice-oriented decomposition. Also, many approaches for microservice decomposition have been proposed. Software teams occasionally felt overwhelmed in their daily work, where the business changes seems out of their control. The first software organization are keen to improve DevOps pipelines, but may have less interest in the essentials that DevOps advocates for the holistic improvement. The complete DevOps pipelines were dedicated into several segments that are barely consigned to each other. The first shapes is between planning and coding. The shapes resides questions about whether DevOps is indeed a dropped-in organization because of the description of Dev and Ops. Some software teams do not need to use the complete DevOps pipelines in their daily work. Consequently, they only care about the protection of the pipelines that they are involved in. Second, departmental barriers still exist in these cases deeper than ever. Given the uncertainty of the assessment in some cross-team tasks, software teams tend to make their own interesting development. In the observation, the three companies also there exist knowledge sharing platforms. Software teams perform to share the techniques and methods within their own team rather across team, which might complicate the learning process for other teams.
I think we need to go to your conclusions. We're quite a bit behind.
Okay, our observation and interviews require that in some software teams, the relationship between DevOps and microservice is not significant, which differ from the relationship description in previous studies. The conclusion: our findings contribute to the understanding of the organization benefits and issues of dropping DevOps and microservice from immense perspective of software teams. Thanks everyone for listening.
Thank you very much. Our next speaker is Lanxin Yang, and the talk is titled An Industrial Experience Report on Retro Inspection. Very good. We can see your screen share. And you just need to unmute your microphone. Should be on the lower left.
It's on the lower left, actually really close to where you start sharing your screen. Yeah.
Okay, I see.
Okay, good. Now we've got the microphone. Now we need the screen share.
Yeah.
Okay. Is that okay?
Perfect.
Okay, thank you. Hello everyone, my name is Lanxin Yang. It's my honor to be here. Today I'm going to report on our paper, an industry experience report on retro inspection. Quality assurance has always been highly concerned in software development and maintenance. In most cases, although all the code commits merge into project repository subject to review and testing, there are residual defects which consume significant time and effort to fix. A few teams at this enterprise organized informal postmortems and other type of simultaneously retrospective style meetings to solve such challenges. This type of practice to some extent conferred its effectiveness in ensuring software quality and therefore attracted officials' attention. Having surveyed pilot teams and discussed with the QA and audit divisions, this practice was officially acknowledged and standardized. Finally, this enterprise has officially institutionalized such a retrospective style inspection, namely retro inspection, in this paper, a mean to reinforce the quality of code delivery, especially to improve future coding quality, and to foster developers' awareness of quality concerns. In a nutshell, Ritual inspection is an enterprise-specific practice for software quality assurance, and this practice is a variation of classical figure inspection. Also, it shares many similarities with peer code reviews, but differs in purposes, samples, participants, stages, processes, and activities. For example, for the stages, peer code review is mandatory within divisions prior to merging code commits into project repository, whereas ritual inspection is optional and should be conducted by external divisions after testing has been completed. This study aims to investigate the experience and lessons from ritual inspections. To this end, we proposed 4 research questions. ARC1 is related to the benefits. ARC2 is related to the common styles in ritual inspections. ARC3 concerns the defect types and the severities. Finally, ARC4 concerns the lessons learned from ritual inspections. In this study, we collected and analyzed various empirical evidence for data triangulation. To be specific, we performed archive analysis, questionnaire surveys, and panel interviews during the data collection stage, and we conducted descriptive analysis, thematic analysis, and narrative analysis during the data analysis stage. For the first research question, we found that in addition to its major function, that is code quality assurance, especially for future quality, ritual inspection can contribute to side benefits such as internal audit, inter-division communication, and additionally plays a role in cultivating developers and reviewers. For the third research question, we found that comments in ritual inspection clarify defects, elaborate rationale, offer suggestions for assisting correction and improvement, as well as appreciate those well-done work. Despite some of them also appears in peer code reviews, they are more common in ritual inspections. For the third research question, we found that multiple software experts collaboratively examine the sampled projects in ritual inspections, identifying a wide range of defects such as logic faults, security vulnerabilities, as well as violations of coding standards and coding experience. Quite a few of them are serious and should be highly considered, which confers the unique value of ritual inspections. Finally, for the last research question, we found that despite its many benefits, ritual inspection also suffer developers' acceptance, inspectors' engagement, and organizers' predicament. Therefore, it has not worked completely as expected and needs improvement. Accordingly, in this study, we proposed 4 recommendations for improving the future quality of ritual inspections, which are stricter admission criteria for the projects to be inspected, more adequate preparation for both the inspected divisions and the inspectors themselves, longer inspection period so that each role can better complete his or her work. Finally, more careful publicity so that each role can benefit from ritual inspections. In a nutshell, this study reports on an empirical investigation on ritual inspection as an altered career practice in an industry context through long-term observation with data triangulation, which offers reference value for other organizations with serious concerns on software quality. Okay, that's all. For more details, please refer to the preprint paper or contact me by email. Thanks.
Thank you. And as I should have mentioned in the beginning, of course, all the papers are available online. Now I would like to introduce somebody who has been very patient throughout this whole session, and that is Vijay Murali. His talk is titled Improving Code Auto-Completion with Transfer Learning. So Vijay, you can feel free to unmute your mic and screen share.
Yes, actually, I'm just trying to get the screen share to work.
Yeah, it seems to be a challenge.
So, what is the issue actually? It's like, I think when you click there, it should be like a browser pop-up thing.
Yeah,
But,
so it says that it failed. So I have to give permissions from, I'm using Mac OS.
So, okay, let me see here. I think if you go to security and privacy part of your macOS, I think there must be something related to permissions there.
Security settings, got it. Security and privacy.
Yeah, that's perfect.
All right.
It should be like screen recording part.
Let me just try. Yeah, screen recording and I guess Google Chrome.
Yeah, then you start your browser there.
Okay, so it says I have to quit and rejoin. Oh, okay. Try to come back again.
Okay.
Well, I guess in the worst case, you can give the talk without the slides.
But I think that's the issue of the OS. It should be working right now.
While we're waiting, I'd suggest to the speakers that you start to take a look at the questions in the chat session. And in the worst case, if we run out of time, try to make contact offline.
Yeah, now it's working.
Can you now see my screen?
Yeah.
Yes.
Perfect.
Okay. Yeah, sorry for that disruption.
Problem.
All right. So my name is Vijay Murali, and I'm going to be talking to you about improving code auto-completion with transfer learning. So auto-completion is this universal in IDEs or love to hate, but really it really makes coding delightful. It improves developer productivity, and it's an integral part of IDE experience today. So today, auto-completion is powered by language models such as GPT-2 or GPT-3 today, Codex, Copilot, and all of these really large and powerful language models that have been trained on really large amount of data. Now, the problem with deploying auto-completion experience in large industrial settings is that we have to cater to a large and diverse developer population. This developer population is using different coding tools. They're working on projects that are in different stages of development, and they also use different programming languages for their projects. So there is this lack of sufficient training data. We cannot assume that there would always be training data available in terms of the auto-completion selections from developers for all settings in this kind of a large industrial workplace. So the question that we're asking in this work is, can transfer learning help alleviate this problem? And transfer learning is the ability of these kinds of language models to transfer knowledge from one domain or one task to another task. So essentially, we're exploring whether transfer learning can help across this kind of a problem. So in this study, we investigate the performance impact of transfer learning on auto-completion across three particular dimensions. The first dimension is across the learning task. So here we are asking the question, can we train these language models on one particular task and use it for the task of auto-completion, which could be slightly different from the original task on which the model was trained. In the second dimension, we are asking the question, can we transfer learn across source code domain? So, a snippet of code goes through various stages. It could be appearing in an IDE as the developer is typing. It could appear in a code commit. It could appear in a post. So can we actually transfer knowledge across the places where the snippet of code appears and help towards the auto-completion? And the third dimension we are trying to look at is transfer learning across programming languages. Can we learn from one programming language and use that trained model in order to power auto-completion in a different programming language? The metrics we are using in this study are of two kinds. For offline evaluation, we use the standard top one accuracy. And we are essentially here measuring how often the model is assigning the highest probability to the selection that was shown to the user and the one that they actually chose. In terms of online evaluation, we are actually deploying this kind of an auto-completion system in the company, and we are measuring the mean value of daily completions usages per user. And this is like across test and control groups in a large scale kind of A/B testing kind of environment with some statistical significance measures. So across the first dimension, we are looking at transfer learning across the learning task. Here, the problem is with the accessibility of training data. So when developers are shown these kinds of auto-completion suggestions and they end up selecting, this kind of data is not always possible to be logged. This could be due to various reasons ranging from privacy to performance of the IDE itself. And therefore, we cannot expect this data to be logged all the time. And therefore, this data may not be available for training auto-completion models. However, on the other hand, we may have access to just unlabeled snippets of code that could be obtained from the company's repository of code. So the question here is, can we actually transfer knowledge from these unlabeled snippets of code over to auto-completion usages? And this would entail pre-training a model on these kinds of randomly sampled snippets of code that are unlabeled and fine-tuning the model on maybe a smaller subset of auto-completion selections if the data is available. So on the right, as you can see there, we notice that this pre-training that we can do on this randomly sampled snippets of code, this actually boosts the accuracy of the model by a statistically significant margin. For example, in the top one accuracy, we went from 36% or 0.36 top one accuracy to 0.41. And it also had an impact on the online metric in terms of daily the completions accepted per user. Now, looking at the second question, can we transfer learn across source code domains? Here, code goes through various stages, like I mentioned, could be present in the IDE, where the developer is actively editing it. And it could also be present in a commit that the developer has made after typing the code. And there is an intuitive relationship between code as it goes through these various stages, right? So here, can we transfer learn from commits and power an auto-completion model? And this would entail pre-training this kind of an auto-completion model on code that's present in commits and fine-tuning it on auto-completion selections if they are available. Otherwise, we essentially just use the pre-trained model itself. And again, over here across this dimension, we see that the pre-training does help, and it again results in statistically significant improvement towards the model. On the right, you can see the plot where we measure the performance of this model based on the number of auto-completion examples that are present during fine-tuning. And towards the left of the plot, you can observe that the difference between starting a model from scratch versus starting it from a baseline that's trained on commits, that difference is pretty significant when the number of examples that are available are small. So this means that when the data set is scarce, it makes a lot more sense and a lot more beneficial to train the model on these kinds of code snippets that are present during in code commits, as opposed to using the auto-completion examples directly. And finally, we are asking the question of transfer learning across programming languages. And over here at Meta, there is an uneven distribution of programming languages, and this is common across large industrial settings. For the auto-completion experience to be uniform, we want to support all of the languages as much as possible. So can we actually train an auto-completion model on one language and use it to power suggestions in a different language? For this, we picked Hack, which is like a flare of PHP that's used in Meta, and Python as the two different programming languages here. So we are comparing a model that's pre-trained on Hack, IDE and code sequences, and potentially fine-tuned on Python if we have those examples. Otherwise, we directly use the Hack model to power auto-completion suggestions in Python. And we are comparing the performance between a model that is trained from scratch on just the examples that are available in Python versus one that's already been trained on Hack, and incrementally we are adding more examples from Python. So this is the plot on the left that you see. And again, you can see that the difference, while not as significant as before, there is still non-negligible difference between starting a model from scratch versus using a model that's trained on a slightly different programming language. And towards the left, you can see the difference is again pretty significant if the number of examples from the target programming language are small. So the takeaway from this work is that training and deploying these kinds of auto-completion models in a large industrial setting is not straightforward because of all the reasons that I mentioned. And transfer learning, which is a very inherent property of these language models, can help mitigate the issues with the scarcity of labeled examples that are available from auto-completion. And we explored 3 dimensions across which transfer learning can help across the learning task, across source code domain, and across programming languages. Thank you.
Thank you very much. We've had a couple of questions that were asked and answered in the chat session. Are there more questions or discussion items? Everybody's being very quiet. I know we certainly had some technical problems here. Once again, all the papers are available online, and certainly with the social hours that are built into this and coffee sessions, it's very easy for us to go back and reference things. So I'd like to thank all the speakers and the audience. If there are no further comments, we'll go ahead and end this session. Once again, thank you very much.